Okay, we need to talk about work because this is where thermo. My computer just just started up. This is where thermo begins because this is dynamics. This is physics. But here is where thermo really truly begins right now. Because in work, thermo has a sign convention. Okay, and we have to worry about this sign convention. Work done by a system to the surroundings is going to be considered positive. And work done by the surroundings on the system is considered negative. Now, right now, that may not mean a lot to you, but look at this equation. If a system is giving work to the surroundings, what is happening to the energy of a system? It's going down. But we're calling that positive. That's opposite of what this equation would tell us. Okay, if we take something away from the system, the energy is going to be removed. We're saying no, that's positive. If we're taking the surroundings, are putting work in, transferring work into the system, that should be positive. We're saying that's negative. Why? Why would in thermodynamics we do this? Well, in thermo, we want systems to complete work. We want it to do work. Okay? We want that to be a positive. I drive a 2004 Dodge Dakota. It has a 230 horsepower engine. That's the power. It's related to work. I do not say that is a negative 230 horsepower engine. That's really what it's doing. It's taking energy out of the fuel. No. We consider that positive. It is creating the system to the surroundings could create 230 horsepower. Okay. Now this sign convention can potentially cause you to start off in this class some issues. Okay. So here's what I'm going to ask you to do. I'm going to ask you to start writing this equation like this: delta KE plus delta PE is equal to, and then we're going to put here a minus the summation of all the work. Okay, now it's the same equation, but now we put it on the other side, and what we're doing here, this is going to be, you add up all the works. Okay, so you might have 3 or 4 different forces acting on it. Add it all up. Okay, inside this parentheses here, inside this magical parentheses goes the thermal sign convention. Goes inside the parentheses. And then what happens is we go ahead and put a negative sign here to flip the sign back to the way it should be. Okay. So this is my analogy in here. I may have a personal sign convention about money. I may say that gaining money from the surroundings, people giving me money, is negative. But I may think that giving money away is very positive. That's my personal sign convention. That's what goes inside the parentheses. Now the equation, the way the bank works is the way the world works. If I give out money, my bank account goes down, and if I get in money, my bank account goes up. So this sign flipper here is a bank teller. If I walk into the bank and I'm really sad, I'm saying, here's my paycheck. That's kind of negative. I'm just giving something. I like to give things away, but it's coming in. The bank account teller is going to say, okay, you put into your sign convention, you put in a negative, but I'm going to put a negative on the other side to it that's going to come out as a positive, and your bank account is going to rise with the amount of money in it. If I come to the bank teller and I say, hey, I would like to take some money out, I want to give some money away, and I consider that to be positive, the bank teller is going to say, that's fine. They're going to put that negative sign on it because that's the way that the bank teller always works with my sign convention, and this is going to come out negative, which is exactly what's happening. Okay? The equation that we write here, we're taking a thermodynamic view. We can't change the way the world works. Just because we want to call something positive that's actually negative and something negative is actually positive, we can't change the way the world works. So we have to edit our equation so it works for us, and that starts to give us our new thermodynamic equation. Okay, so remember this again. Work from the surroundings into the systems increases the energy of the system. Work from the systems out to the surroundings decreases the energy of the system. All right? That's how we deal it in thermodynamics. That's how we work with it in thermodynamics. All right. Now, question I want to ask you here about work. Is work a property? Is work a property? That's going to be your question that you have to answer here. Is work a property? And let me give you a little, let me have you do something, okay? And I want you to pause you can do this if you want to, but remember, properties, it only cares what happens from state 1 to state 2. Okay, you don't care about anything that happens between there, you only care about state 1 and state 2. Let's talk about work. Work is the integral from 1 to 2 of f dx. Okay, let me ask you this question. Wherever you are right now, I want you to put two, in whatever room you are, I want you to put two states, state 1, state 2, 2 locations, okay? One corner of the room to the other corner of the room, right? Then I want you to take a time, and I want you to walk from state 1 to state 2. Now, after you do that, I want you to go now start at state 1 and go to state 2, but this time don't go directly to state 2. Go out the door, run around your house twice, and then come back out and go to state 2. And then I want you to come back and sit in your chair and see how about your breathing. And ask yourself, did you do more work in process 1 or in process 2? Or did you do the same amount? If work is a property, it should not matter how you get from state 1 to state 2, you do the same amount of work. If work isn't a property, then that you do more work dependent upon the path. Okay, dependent upon the path. Okay, that's what I want you to figure out. Is work a property? Let's end that video right there and we'll move on to our next thing.